record this computer and we start recording.
All right, can you see it?
Yes, we see your screen. Yeah, now you can put full mode screen now.
Okay.
Yes, like this. Yeah.
So I can start?
Yes, please. Yeah.
All right. So my presentation is on looking at the aerodynamics of Formula One cars and specifically how the wake of the car is produced. So as the car is moving through air, what kind of wake is generated with the car passing through the air, and different strategies that the teams use and rules use to, well, for future cars, mitigate the wake. So the first slide, the car I'm showing here is the Mercedes-Benz 2020 car, and they have been the champions the past 6 years. So they're kind of the leaders of Formula One and developing like the aerodynamics. So the two factors that we're looking at is how the car produces a wake and clean air, and then how that affects the trailing cars behind them. And then for the 2021 rule changes, which is being moved to 2022 with the season being delayed so far, what they're doing is the cars on the underside, they're changing how the body is to, further or to try and reduce the wake and the angle that the wake is produced at. And I'll show you a slide later on that shows that visualization. And then also they are limiting limiting wind tunnel testing and transitioning to a major focus on CFD for the cars. And then also they're redesigning the wheels. Since these are open wheel cars, the wheels, they cause a lot of drag. So they're changing how the wheels are designed to try and mitigate some of that drag and how that affects the wake. So the top right picture is a very basic demonstration of the airflow. So the front wing pretty much is what is going to direct the air. So either they're going to push air underneath the car or over top of the car. And as you can see, the outsides of the front wing, they're trying to push air over top the wheels so that the wheels can't cause disturbances. And then at the back of the car, the rear wing, depending on like what part of the track it's in and what speed the car is moving at, the wing will adjust to either allow for more downforce and cornering, or on straight stretches, the wing will pretty much open up and reduce the drag so the car can have a higher top speed. And then, like I just mentioned, the wheels, they cause a lot of drag, so that's why the front wings can try and divert the airflow away from it. And then underneath the body, with how the tunnels work, pretty much those tunnels work to pull the car, or to suck the car down onto the ground, so they have better downforce. And then the bottom right picture is showing the Mercedes-Benz car on the left and the Ferrari car on the right. So it's just showing like the variation in the front wing design and how the cars are all different from the aerodynamic standpoint. So I just wanted to, so Ferrari is the second best team, and they have been for the last 3 or 4 years. So these are just showing the differences in the top two cars and how they have completely different designs. And even though they have completely different designs, they're still the two best teams in Formula One. And then, so talking about downforce and drag, so this was the most recent published study I could find. There's not many public studies on Formula One, since these are all private teams competing and pretty much everything is kept in-house. Each team does pretty much their own development of the cars. There's certain rules that they have to follow, and there's certain components of the cars that have to be there. But then pretty much on the aerodynamics, they have full range as long as they're inside of those dimensions that the car fits in. So from a downforce standpoint, the underside of the car produces, for the 2009 cars, produce 50% of the downforce. So, that's, when I would look at the car, I would think the wings are producing the most downforce, but it's really the underside design of the cars. And over on the right-hand side is showing how the next-gen cars are going to have that increased downforce. So you can see these tunnels for the 2021 car versus the current style where it looks like it's more of a flat surface. And you can see how the wheels are differing between the 21 car and the current car. And then from a drag standpoint, the front wing and the rear wing have the highest drag as I kind of expected it would. But then the next biggest contributor of that is going to be the wheels and the suspension. So again, like I said, moving into the next year's rule changes, they're trying to reduce the drag that the wheels have on the car itself. So this is showing kind of a development of the wake. So the top right picture is showing the current car and then the next generation car. So that bottom, so like the bottom section, they're trying to clean up the air down here. So as a car is trailing behind a car, they're going to have better downforce. So as this car, so there's a car in the front over here on the left-hand side of the bottom picture. And then that car is going through the clean air, which is kind of representing these blue dots. And then the red arrows are showing how the air is going to actually move. So they're showing kind of like the vector of how the air is going to move after that car passes through it. So since this trailing car is not going to have that clean air to move through, pretty much you're going to have, they have reduced downforce. So depending on how close that trailing car is, they're going to have a certain percentage of the total downforce that they could have if they were in the clean air itself. So this was a study done on a 2011, the 2011 Formula One rules. So they were doing wind tunnel testing on a model, and they were looking at how trailing or how the velocity of the car changes right behind the model, and then half a car length behind the model, and then a full car length behind the model. And they were looking at the velocity measurements to be able to determine or determine how the velocity profiles are changing and the turbulence intensity. So one of the limitations that this study had was there's pretty much no downforce generation from the under side of the car with how the model was set up. So the study was pretty much only looking at the top side aerodynamics of the car, so the front wing, how the tires interact, and then the rear wing, and obviously the body of the car. And then so the top right graph is showing the normalized velocity distribution. So on the left-hand side of the equation, the top equation, you can see they're taking it's the local velocity divided by V infinity. So they're showing the deficit in velocity, and then where there's a deficit in velocity, we're going to have that's where the turbulence is generated. So you see the mushroom cloud down on the right-hand side, and out in the free stream, we're not going to have any turbulence. But as you get closer to where the car is, it's going to develop turbulent regions, and it follows this mushroom cloud shape. And then you can see the vortical structures in the bottom left picture. Of how like the air is being generated and moving off of the car itself. So here's some more things off the study. So this bottom left picture was showing how the wing itself is going to start generating turbulence. So they took one of the smoke tubes and put it right in front of the wing and had the air flowing over it. And then you can see how the wing is going to generate this wake and, cause the turbulence to develop and happen behind the car. So the top right picture, that is from following at half a car length behind the model. And then the bottom picture is at a full car length. So pretty much half the distance of the car, and how the turbulent intensity is going to change. So as expected, the turbulence intensity is going to drop as you move further away from the car, just because the turbulence has time to die out. And then also kind of the structure to go into start expanding as well, and start moving upwards as it moves away from the car. So that's one of the things that they're trying to do with the 2021 rules, is they're trying to make sure that this mushroom cloud profile is going to move in positive in the Z direction, further up away from the cars as you move away from the car to have, try and have undisturbed air trailing the cars. And then this is showing how, so they had three different wing profiles, rear wing profiles. They had one that was kind of their baseline design. And then they had a second wing profile, which is -15 degrees of an angle of attack. And that wing profile didn't show much in change for like the size of this mushroom cloud, turbulence region to develop. They saw that the cloud size had increased in size, and it increased about 0.3 meters. But pretty much the structure and everything was still the same between the baseline and the -15 degree. And then these pictures, the two pictures on the right are an angle of attack of -47 degrees. And so here they're seeing that, the turbulent intensity is decreasing. So you can see that the size of the mushroom cloud is changing. And you're seeing that for both the normalized velocity profiles and the turbulent intensity profiles. So they saw that the turbulent intensity decreased about 30% with the angle of attack at the -47 degrees, but the velocity, there's a velocity deficit of about 13%. So that was kind of following what they were expecting to see. But pretty much, kind of the thing I wanted to point out is how the structure has shrunk a lot for the two right profiles compared to the baseline profile, and just that the intensities were changing. But that's pretty much my presentation and my sources, and obviously I can take questions.
Okay, thank you very much. Thank you. So please questions from the audience first. So for
sorry. Yeah. Hello, Christian.
Hello.
All right. Yeah. You said if a car is coming behind another car and does not encounter the clean air that the first car encountered, that's going to reduce the downward force experienced by that car, right?
Yes.
Okay. What about the drag experienced by that car? That will be reduced too, isn't it?
The car, the
drag.
second car, yes.
Yeah, the second car, yeah.
Yeah.
So meaning that that car might use less fuel travel the same distance because it experiences less drag.
Mm-hmm.
Yeah. So could that be an advantage or a disadvantage? I mean, the fact that it's not encountering the clean air, is that an advantage for the car or a disadvantage?
So it would depend on the track. So a track that would have a lot of straightaways, that would definitely be an advantage for the trailing car, because obviously you're going to save fuel. Like
okay, yeah.
But on a track that's going to have a lot of turns, you need the downforce.
Exactly, so that you can turn easily and don't skid off the road. Okay, it makes sense. Yeah.
Yeah.
Okay,
yep.
Thank you.
And then teams will use that if if the same racers from the same team are right behind each other, they can trade off on going on those long stretches out in front and trying to save fuel.
Okay. Yeah, that makes sense. Thank you.
Okay, please, more comments, more questions, please.
Who's your favorite Formula One driver?
Daniel Ricciardo is my favorite one, and then it's hard not to like Lewis Hamilton just because he's won so many.
Yeah, Hamilton's nice.
Yeah.
Cool. That's all I had.
Okay, please, more questions? Yeah, please. Well, in fact, it's good. It's good that you make this presentation. And as I told you, it's curious that every year, like we have different students, different type of presentations, but topics covered are really quite similar. Like last time we had a talk about, yeah, many students select like something from the work, but many students select something from common life, common practice, industry, science, and it's nice. Like last time, Gadi talked about blood pressure, blood turbulence, and every year I had one or two presentations on medical applications of turbulence, particularly really what happens in capillaries. And every year really like I have a presentation on typically either like Formula One or like something like drag forcing of cars, or and the same concerning airplanes, spacecrafts, fleet, something like this. And so that's really, it means that really it covers turbulence, and it's really covers all the interest, why people take this class and why people are interested in turbulence. So regarding your particular, so could you please go back to in your slides when you talk about intensity? Just I wanted to check if you go back, please, back the slides more when you have formula. So yeah, here. So let me just check here. So you say you have normalized velocity, right? So
Hmm.
what is velocity at infinity? Where do you take it? Where, how it is measured here? What is velocity?
So where are they measuring the V infinity?
Yes, what is it?
So they didn't state what the V infinity was, but they gave a Reynolds number. So they went through some different Reynolds numbers and found where you know the model behaved accordingly to how the other studies had behaved. So that's where they found a Reynolds number of the 2.4 times 10 to the 6. But they didn't specifically state what the velocity was with respect to that.
Uh,
Yeah.
Hello, I think V infinity is usually the stream velocity. I mean, far away from the body that you're studying.
Yeah,
Uh-huh. Hello,
yeah, but I didn't. They didn't state what the
what it was.
V infinity was.
Yeah, and Reynolds number is pretty big. It's about million, right? Like wasn't million, but you're
Hmm.
saying it's really big. So what about, so then you calculate average velocity, like root means it's like root. So velocity average, it's actually what? It's like, what is n here? So you take summation of root squared velocity. It's root, let me calculate. Is it like, yeah, you take root mean square velocities divided by n, right? Uh-huh.
Yeah.
And
Hmm.
what about like I? What is next? What is next term? What
So
is
that was the turbulence intensity.
aha? And sigmas were like deviations, standard deviations, right?
Yeah.
Mm-hmm. I see. I see. Okay, thank you. If you go back, so yes, and that is streamlines, and in this color. So what this color mean in these pictures?
The colors. So it's hidden behind. I don't know how to move the boxes where the people are, but the colors are showing kind of like the intensity. So for the velocity intensity, the white background is going to be the average velocity divided by the v infinities equal to 1, so it's the same. So as the colors go from the white to yellow to orange to the purple is going to be the lowest velocity compared to the streamline velocities at the infinity.
Okay, very well. Yeah, I see. I see. I see. And could you go back one slide back? Or two slides back. Yeah. So yeah, here's some kind I missed it. So what's this like? No, no. Next slide.
This
Next.
one?
What? Yeah. So what's this? What's next? Next. Slide number 5.
Okay.
Yeah, here it is. So what this like circle, this sphere, small spheres mean by color? So what are they? What is pink? What is blue color?
So the bluish green color, that's going to be air that's undisturbed by the car. And then the red with the with the arrows, that's showing um, air that's moving because of the cars and then what direction it's moving. So as the cars go by, due to the friction of the car going through the air, it's going to start pulling those stationary particles along with the car.
I see, yeah. And when you say dirty air, and so I know what is dirty air, but what different colors mean here for dirty air? What is blue? What is green?
So red's the clean air for the bottom picture.
So okay, so green is like clean air, and red and blue some deviations from it, right?
Yeah.
And yeah, and okay, and what is red?
For which picture?
So picture upstairs.
Oh, upstairs. So that they didn't have like a scale on what the values are, but pretty much what they were talking about is how the bottom part where they have these white arrows, they're pretty much, that's where they're trying to divert the wake at a higher angle. So as a car moves closer, it's going to have it's not going to have as much turbulent air from the car in front of it. Whereas the current cars, they still have these profiles down here instead of the air moving up towards out of the path of the car that's moving.
Okay, thank you. Okay, any more question? Okay, if not, thanks again our speaker. It was really good presentation. So let me stop recording now, and